thank you all for the invitation to come and speak to you. I've never spoken or presented as far north as Svalbard before. I would love to have had the opportunity to do it in person, but instead I'm coming to you today from Copenhagen, where it is getting somewhat cold outside, so maybe the weather is at least making me feel like I'm getting a long way north. What I'm going to be talking to you today about is the work that I've been doing looking at ocean predictability and how that relates to ocean observations, and how it all links up with the United Nations Ocean Decade. And if there's one thing that I think we all, question that we all have about climate change and climate variability, it's essentially is what will it mean for us? And if we think about these questions and about the future, and trying to think about how we respond to the future, it obviously depends on who you are and what your interests are. You could be, for example, a fisher that's dependent on particular fish stocks and would like to know where they're going to be and how their abundance will change. Maybe it could be a local community, such as here in Longyearbyen, that's dependent on having ice-free harbours and needs to know both when they're going to be open. Similarly, it could also be scientists that need to have access to that type of information. Or maybe it could be the captain of a ship that needs to navigate through the Arctic and make sure that her crew and her cargo gets through safely. And so when in all of these cases, people and their stakeholders can take their questions to science and to scientists and say, what can we expect to see in the future? And one way to think about these questions is essentially in terms of timescales, ranging from days and weeks out here on the left-hand side through seasons, years, and decades into the future. And there are many, many different questions and timescales involved. And science is very good at doing this sort of short timescale, days and weeks. These are weather forecasts. We're very good at predicting the atmosphere and the ocean on these short timescales. And we've got to be very good and done a lot of work looking at these long timescales, at the decadal and centennial timescales under climate change. But there's really a gap that exists on this sort of months to seasons to years timescales. And this is actually where many parts of society have their most important questions about how you do strategic sort of longer term planning. How many people should I employ in my business next year? When should I place an order? What is the potential for fish catches, and how should I plan accordingly? And up until this point, science and the scientific community hasn't been very good at plugging that gap. But that's changing. And we actually find ourselves in the middle of essentially a scientific revolution. It's taking place quietly, far away from the literature most of us read, but it's a revolution nonetheless. And what this revolution is that today it's possible to predict the ocean skillfully months and years ahead. And I have here an exact example of this type of forecast. This comes from the Copernicus system, and it's a forecast for the sea surface temperatures and averaged over February, March, and April, essentially the spring temperatures next year. And I've shown both the map of globally and also of the Arctic. And in particular, one thing that you'll note here is this big blue anomaly that's sitting out here. It corresponds to a strong La Nina condition that's essentially being forecast for the coming months. And this is, of course, is very relevant to all of those that are dependent on the ocean and for its consequences for society. The question that you then ask is why and how can we do this? And a 6-month weather forecast, that's unheard of normally. And the reason that we can do this is essentially because, the reason we can do this is that there's been substantial advances in different parts of science. The first and perhaps one of the most important is there's been substantial advances in observations. And I'm sure most of you are familiar with this. We have Argo floats, we have remote sensing, we have gliders, we have buoys. We have many more ways to measure the ocean, and the volume of data that we have available to us has increased dramatically over recent years. The second point that's important is that we can have climate models have also got better. This is due to obviously the vast increases in computational power, but also due to things like our ability to represent processes, such as cloud dynamics, and the development of ensemble techniques in particular has been very, very important. But the third and most important part is actually the idea of data assimilation, that we can take the observational data and actually put it into the model. And this in principle should be relatively straightforward. But for anyone that's tried to do this during their life, you'll know that it's not quite as easy as it looks. So it's really the combination of these three that have driven the ability to make these forecasts. So given these ocean observations, I've shown you that we can actually forecast the state of the ocean. But what about society? Can we actually take this further and make forecasts that are relevant for stakeholders and for decision making? And the answer to that is very clearly yes. And I'm going to give you a couple of examples of that from my own work. The example is actually the catches of bluefin tuna in Greenlandic water. This was inspired by a very unusual observation of the catches of these tuna here on the left-hand side in August 2012. And we saw this again in August 2014. And what was unusual and extremely strange about them was where they were caught, right here in the middle of Denmark Strait. And this is an extremely unusual place to find bluefin tuna. Normally, they're essentially off the bottom of that map in warmer waters in the Western Mediterranean, for example, or the Gulf of Mexico, where they spawn. And we went through the literature and investigated this, and we found that this was essentially the first ever report of tuna in this area for at least 370 years, and probably the first documented report ever that we could find. So the question is what were they doing there? Well, we were actually able to develop a habitat model of the species and then actually look at how the habitat has changed both in the past and into the future. And so this is essentially what we've plotted here. On the left-hand side, we have the area of suitable habitat, and this is against time. And we can see that there's essentially a step change that takes place here around about the year 2000, with a substantial increase in this region of the amount of suitable habitat. And the years where we observed tuna were essentially these two, which are amongst some of the warmest years on the record there. And then we can actually take this and couple it to the forecast models that we talked about and start to look into the future. And so in particular, this is from the outputs from a set of decadal forecast models, looking essentially up to 2025. And we see that there's essentially a relatively low level corresponding to this increase, but certainly nothing compared to these tuna years. And then to put that into the long-term perspective, we can actually run it all the way out into the future to 2100 under either a business as usual scenario or a Parisian type of agreement. And so we can see that we expect to see substantial increases in the amount of habitat in this region. But certainly these higher years are not really repeated until mid-century. So this actually, the interpretation that we take from this is that we see it's unlikely that we'll see tuna in Greenlandic waters during the next decade. And this is obviously something that's of direct relevance both to Greenland and to Iceland, and the questions of whether they should start to think about actually trying to pursue a fishery on this particular fish stock. And so we've actually used this type of logic and forecasting thinking in other instances as well. I have two more examples here of forecast products that I've issued recently. These are both forecasts for what will happen next year. On the left-hand side, we have a forecast of the distribution of blue whiting, which is a commercially important pelagic fish species. We're forecasting a distribution essentially in this region compacted up against the continental shelf. And on the right-hand side, we have a forecast of recruitment, or the number of juveniles that are produced in a fish stock for 2021. This is for sand eel in the North Sea region. But we're also in the process of developing similar forecasts for the Barents Sea cod stock and many other cod stocks around the world. And so this is actually a good example of what we can, of what we can do with predicting things that are relevant to society. And this actually links up very closely to the work of the United Nations Decade of Ocean Science for Sustainable Development. And if you're not familiar with this, the basic idea is it's a UN global initiative to try and focus the work that we do and to bring our science together so that we can actually deliver the ocean outcomes that we need. And within the Ocean Decade, there are 7 outcomes that are identified. You can see I've listed them here down the left-hand side. And one of these is actually the idea of a predicted ocean. You need to be able to have this foresight and knowledge about what the ocean will bring as a way to drive sustainable development and to support the communities that are highly dependent on the ocean. And so within this, we actually have a process ongoing to develop an action plan for Arctic and high latitude regions that's currently under development. And I'm actually leading the development of the predicted ocean section together with Sandy Starkweather from NOAA, who many of you may know. One of the main guiding principles that we've taken in this is essentially based on the idea of a value chain, running essentially from observing system inputs out here on the left through intermediate products such as the outputs of sea surface temperature forecasts, which I talked about, through to applications such as the types of fish forecasts that I have just talked about, and all the way over here on the right hand side to societal benefits and gains for society. And so this is a very useful and sort of guiding way to think about it. Perhaps the most important thing that we need to remember when we're thinking about this is that when we're developing and trying to make forecasts, a good forecast is one that's used to make decisions. And in particular, it's the users, therefore, that are the judges of whether a forecast actually has value. Whether or not a forecast is useful or useless doesn't have so much to do with its scientific quantity. It's whether it meets the needs of society. So this means that when we're approaching this type of work, we need to collaborate right from the very start. We need end users and stakeholders and rights holders involved all the way through the process to specify, to develop, to help design the project, the forecast product, to think about how we communicate it and how we essentially work in this as co-production and co-development mode. So if I sum up, we have, I hope I've convinced you in this rather quick tour around ocean predictability that we can predict the ocean. And we can not only predict the ocean, but we can predict things that are relevant to society, such as biological responses. But if we want to keep doing this and do this better and have impacts on society, we need to make sure that our science is linked up all the way from the observations to the forecasts to the societal benefits that we actually hope to achieve. And in particular, this process needs to be guided and drawn by the needs of society so that we make sure that our science and our forecasts and our observations are relevant to their needs. So with that, I thank you for your attention and ask if there are any questions.
Then thank you very much for inviting me. Well, my name is Alejandro Orfila. I'm going to talk about the European initiative, the Mongoose, that is the Mediterranean Oceanography Network for the Global Ocean Observing System. That is a top-down initiative to share data and experience in the Mediterranean Sea in order to provide, as we have seen in the last talk, the very, very nice talk indeed from Mark, to share experience and to advance in the society needs from ocean observation and ocean forecast. What is Mongoose? Mongoose is an organization trying to coordinate operational oceanography in the Mediterranean Sea. It has a key role in the coordination for modeling and observational components in the region. As Mark told, he says a very important issue, and in the last slide, that was, can we predict the ocean? The answer is yes, we can predict the ocean, but for that, because the ocean is a chaotic system, we need observations. And it's very important to take into account this point. The difference between the ocean and the atmosphere is the same fluid, is that in the atmosphere we had a lot and a very well established observing systems. And that's the point about the future and the challenge in oceanography. We need observations. So Mongoose has an integrated philosophy where observations and modeling in a broad sense are combined to provide also downstream services. As Mark also pointed, very good point. Can we make our forecast useful for society? That's the idea of Mongoose and indeed of the goose systems around the world. So we try to follow state-of-the-art technologies, new technological applications and capabilities. We try to be responsive, as I will tell later. We have a change in the paradigm in ocean observation also now. We include outreach programs, also trying to provide the response to society, and also one very specific and special issue is fostering collaboration at the European level. So the mission of Mongoose is basically to push the countries, the different countries that have a lot of initiatives separately, to involve together the Mediterranean, that is a very specific ocean, enclosed, indeed, very complex enclosed ocean, a very small laboratory surrounded by 3 continents, trying to work together. How? Doing good science to provide to the society the needs that they demand. Fisheries, climate change, plastics, search and rescue, etc., etc., etc. So we try to identify gaps, to put together the knowledge, and to give this response to society. So Mongoose is a collaboration initiative between different partners, 47 partners from 15 countries. As you see here in this map, we have a strong imbalance between Europe and Africa, and we need data because the ocean is shared by all these countries. We need to put a lot of efforts, European society, to fill these gaps, because as you see, we will have many gaps. And there is also a large imbalance between countries in Europe. So we are trying to fill this map with different countries also. The Mongoose is organized in 3 working groups. We have an observing system that is managed by Lauren Coppola in NERSC, and there are different observing systems. We have the satellite observing initiative, the HF radar that is very active in the Mediterranean Sea. We have the tide gauges also, gliders, Argo and drifters, ferry boxes, and the mooring facilities, buoy and mooring facilities, including meteorological and oceanographic waves, and also EDCPs and ADVs. We have the modeling also working group that is led by Sandis Sofianos of the University of Athens, that combines all modeling initiatives in the Mediterranean Sea, and also a very active and very important issue that Mark was also pointing out, the application and relation to industry and society, that is led by Giovanni Copini. So everything can be consulted, everything is public, can be consulted on the webpage. The webpage is at, well, we are migrating now to Eurogoose. I have to say that Mongoose is a ruse from Mongoose, but also is a global regional alliance from UNESCO. So you can consult all the data in the webpage, the HF radar, the fixed stations that are, as I said, meteorological, oceanographic, wave gauges, etc., etc. The modeling also, and the Metargo. about the modeling, there are many initiatives. We're trying to combine all of them in a unique platform, but all institutes have their own modeling efforts by their own necessities. Basically, in Spain are covering the Western Mediterranean Sea, in Greece the Eastern Mediterranean Sea, and the institution from the Adriatic are covering mostly the Adriatic. But all of them are combined in a unique platform that can be also consulted and in the web page. Obviously, the modeling are state-of-the-art models, and we are in a strong collaboration, as we think that has to be in this way, with Copernicus. As I say, also, there is a lack of data in the Southern Sea, and we need this data to run the models, to initialize and to correct deviations from the nonlinearities of the system. So we have to make a huge effort in the following years in trying to include this northern African coast with data. The web page also, in the web page can see very nice applications about the measurements that are provided by the different partners, including, as I say, the gliders, tracks. There are many institutions making continuous glider tracks. There are the atmospheric and the oceanic buoys, etc., etc. Again, inequality of coverage in the Adriatic, in the northern, in the southern basin of the Mediterranean Sea. And well, there are inequalities. So, for example, in Spain, there are a lot of wave and tide gauges, but there is a lack of atmospheric measurements, for example, in the ocean. Everything can be consulted in web page, so I invite you to see. And about as Mark said, the application that is very important, we are trying to impulse and to provide questions to aquaculture and fisheries, tourism, that is very important in the Med Sea also, integrated coastal zone management, and now it's very important with the climate global change scenario, that for transport and harbor service, marine digital service, technology for safety also, climate change, and energy, marine energy, that will be one of the key issues in the following years. What are the actions that we are trying to impulse in the next 2 years? Well, we are including a large involvement of mongoose in the African countries inside mongoose. We try to collaborate with Africa goose and mongoose on fostering connections with the countries. Obviously, we need to transfer technological and scientific knowledge from Europe to Africa. We try to consolidate the relation with Euro goose, Black Sea goose. So everything with other gooses will be more than welcome. Scientific and technological transfer of knowledge will be very useful. We want to consolidate, and we try to consolidate the position of mongoose in the goose framework. As I said before, mongoose is a global regional alliance. And also we want to progress in engagement between mongoose and Siemens and EMODNet, that are the portals for operational oceanography and data in Europe. We want to consolidate, and we try to consolidate the relation with JCOM and IOC, and also with REMPEC, and we want to collaborate in all the search and rescue initiatives. And also very important, we need to implement the biological observation data, imagery and genomics. And just to finalize, I want to show you a different approach. That is a bottom-up approach. That is the Balearic Island coastal observing system. It's very different from mongoose. And this, as I say, is a bottom-up initiative, not a top-down like mongoose. Thinking regionally well, acting regionally, but thinking globally. So it's just a facility of facilities where that is a Spanish initiative, very, very well funded from the Spanish government, trying to make a laboratory in a specific area, the Balearic Sea, to make observation and modeling to provide a response to society. And I have to say that it's a very well-funded initiative from the Spanish government. By the return budget from the European project is almost 100%. And the idea is basically the same ideas as Mongoose and the global ocean observing system, but regionally, and is because now we changed the paradigm in ocean observations. In the last century, observations were based on ship observations and or multi-platform systems, and we have to wait after the cruise to get the data, to analyze the data, to publish the paper. And now we are changing this paradigm. We need data instantaneously. We need reaction, new observation systems, and get the data immediately with quality control, and to provide good data for numerical models or to make predictions. So the oceanography is demanding new challenge, tools, and new developments to get this data. So the SOCIP is divided in 3 main divisions: the science, observational system divisions, that we have the observing facilities, the modeling facilities, and the data center. There is engineering and technological division that is driving the gliders, the Argo buoys, etc., and the society and the science to society divisions. And well, just to finish, well, we have all the new developments, and you can see and consult more, and please contact us in the webpage of Mongoose and at SOCIP that I put here. And thank you very much for being here.
Good morning, everybody. My name is Anton Korosov. I work at the Nansen Center in Bergen, and now I will bring you from warm Mediterranean Sea to the Arctic, and also from under water to space. And I will talk a little bit about remote sensing of sea ice. First, I will talk just briefly what is sea ice, and in general about remote sensing, and then I will try to focus on ice drift and ice type if I have time, and then maybe touch upon assimilation issues. So, as it comes from the name, sea ice is the ice which is floating in the ocean. It is a frozen water, and it starts from floating pancake ice, which are small pieces of ice with a round shape, and then they're growing in size and becoming large pancake ice, and they have this very rough edges, but they are looking like pancakes. That's why it is called so. Then the formation of this ice continues, and there are less water and more frozen ice, and now it is old pancake ice or packed ice. And after that, it is already called first-year ice, and ice which has been created during first year. And now it is a more solid ice pack, and you need a big ship to sail through it. With the winter coming and the ice is getting thicker, but it is still under constant impact from ocean and from atmosphere. So it is drifting a lot, and when the ice is drifting towards the coast, for example, or different ice flows drift towards each other, pressure ridges appear in the ice, making it even thicker and more rough. Also under wind and the current impact, cracks appear in the ice and the leads are forming, and then the water which is opened in these leads is losing a lot of energy and then is transforming into sea ice. So a new ice is forming during the during winter. Very briefly speaking about how to measure sea ice from space, we first have to mention that there are many different instruments in space and the different types of instruments. Some of them are called altimeters. They send electromagnetic wave vertically down and measure the response time. And from that, they can conclude what is the height of the satellite. And if they measure height over ocean and then over sea ice, by this difference, they can say what is ice freeboard or how much it sticks out of the water. And from that, it can be converted to ice thickness. Another very useful instrument is so-called synthetic aperture radar. It is also active remote sensing instrument. It is sending a microwave impulse with some inclination. And it creates not just a single observation in the nadir direction, but an image of sea ice, and usually with a very high resolution. And finally, imaging radiometers are very widely present in space. And they can operate in different ranges of electromagnetic spectrum, meaning that they can see, for example, in the visible, like we do with our eyes, or in the infrared, like thermal cameras that measure COVID temperature do, or even further in microwave. And these imaging radiometers provide information about so-called brightness temperature of sea ice and water and atmosphere, and are also very useful. Here I show just a couple of examples of so-called remote sensing products. A product is some data, usually a matrix of data in some geographical projection, and it is a result of application of an algorithm to raw data that a satellite measures on the orbit. So these products are sea ice concentration on the left and sea ice drift on the right. Concentration shows how much ice is there per unit area, and obviously in the open ocean the concentration is 0, and in the Central Arctic the concentration is almost 100% or 100%, and then there is a gradient. And this image is from yesterday, so we can see that ice has already grown. It hasn't disappeared here. It always stays in the Canadian, let's say, part of the Arctic Ocean, but it has grown already in the East Siberian Seas and in the Kara Sea, and it is coming close to Svalbard. Ice drift product shows how much sea ice drifts or shifts or floats in the ocean, and as you can see, it is not still. It is always in the motion, and the motion is dictated by the winds and also by the ocean currents. So I will now look more into this sea ice drift phenomenon and how we can measure it. So the first systematic measurements of ice drift were performed by Fridtjof Nansen in his famous Fram expedition. He sailed in open waters all the way to the Laptev Sea, and then he has frozen his ship into the sea ice, and then he was drifting together with the sea ice in the hope to reach the North Pole. He didn't reach North Pole, but he achieved so many scientific discoveries that this expedition is super important and extremely valuable for next generations of of Arctic explorers. But yeah, nowadays we have a slightly different approach. Nowadays there are a lot of satellites, and I'm getting back to this synthetic aperture radar. So as I said, it emits a radar pulse, and if the surface is rough, then the pulse is scattered in all directions, also towards the satellite. And if the surface is flat, then it is mostly reflected into other direction and little coming back to the satellite. And when we look at the image from SAR, we can see that the open ocean is flat and therefore it looks dark, but ice is rough, as you could see from the photos before, and therefore it scatters a lot and it looks brighter. Moreover, ice of different types scatters differently, so we can distinguish between pancake ice, which is predominant here, and the more first-year ice type here. And data from the satellites cover Arctic many times a day, so we can use that to observe sea ice drift. This is just an example mosaic of different SAR images taking over the Arctic. And this is SAR, so this is active and a microwave. And this is visible. This is from MODIS. And this is also visible, but this is from Sentinel, which has Sentinel-2, which has very high resolution. So if we start to zoom to the ice near Greenland, we can see that there are many interesting details that we can observe. We can observe some icebergs that are frozen into the ice. We can observe that some ice is maybe a bit more transparent and we can see water through it, and some flows are thicker and look more white. That's in the visible. If we zoom a little bit more, we can see even more details because the resolution of the satellite is very high. But when we switch to SAR, the amount of details is way larger, way higher. So if we switch back and forth, we can see that here these flows look almost the same, but in fact they are all different because they have different surface, different properties, and so on. If we look at several days of observations, we can notice that on the left the flows are frozen and fixed, but on the right they are moving. And that's how sea ice drift looks on this SAR, and we can actually quantify that. How much time do I have left?
You still have 3 minutes.
3 minutes, yes. So in order to quantify that, we take a template from one image, and then we take another image, and then we compare this template from one image and a small part here and compute correlation. And by doing that in several places, we compute a so-called cross-correlation matrix. And then the maximum cross-correlation corresponds to the area where the template from one image matches with the template on another image. So from that, we can understand where the ice has drifted between two images. Here is animation. I will try to run it. So here we can see drift of sea ice, and then by arrows, it is shown the direction and the speed of this sea ice drift. And these arrows are drawn automatically by this algorithm. In order to make this animation, there are 70 images with a total size of 23 gigabytes, and it's a lot of pixels that are needed to be processed with this algorithm. Yeah, I would like also to show this animation. Here we are following one ice flow, hovering over it like a helicopter or drone, and discovering how the ice is deforming and how leads are opening and then are refreezing. And then this information can be used in order to estimate strength or damage of sea ice and assimilate it into models. I will just maybe skip sea ice type, and then I will go directly to the models. So here we can see simulation of sea ice with daily assimilation of sea ice type and sea ice deformation. And the model that is used here is called the NEXCIM, Next Generation Sea Ice Model, and it can very realistically reproduce breakup of sea ice and formation of leads and crack. Thank you for your attention, and if you have questions, please.
Very good. Good morning, everybody. My name is Franco Coren. I'm coming from the same institute of Manuel Benzi. My role in OGS is fundamentally fleet manager for the research OGS fleet. And what I'm just presenting to you today is the research vessel Laura Bassi and some opportunities that we can have in Arctic waters during next year. So Laura Bassi formerly was named the Ernst Shackleton, is an icebreaker class ship built in 1995 with Norwegian design, construction, and construction, has a crew of 22 people and can host up to 50 researcher technicians on board. It's now a category 5 PC5 polar code, so it can operate in Arctic practically between I was thinking about Antarctica. It can operate in Arctic starting from May up to November, and it's a very interesting vessel because it has it's a very balanced capability between cargo and research. It also has a Puma class heli deck on the stern. The vessel itself, in self-arrangement, has a scientific open area here. That's on the stern. There is a facility for deploying rosettes or other scientific equipment. Very vast deck where it can operate a different, it can host different instruments, and a large room for offices and labs as well. The cargo area, the hold area, is constituted by 2 different holds, very capable. We can carry it up to practically 2,500 tons of goods. And into the boat, there is the castle where we have the enlargement for the people. There is a crane of 50 tons that can move the goods from the hold to the cargo hold to the berth or to the ice, depending where you are. And the propulsion system is a very well designed. It consists of a standard prop and shaft system linked to the engine, to the main engine, and 4 azimuth tunnels, and plus 1 azimuth thruster that can be deployed in case of needing. Yes, I forgot to say to you that there's a DP2, so it is a dynamic position second class vessel that can stay practically fixed on a certain point in the sea and maintain its position even in rough weather conditions. Here you can have a quite simple overview of the facility for the fishery or scientific equipment that can be deployed by the stern, and 2 pictures of the lab. On the left there's the dry lab, on the right, the bottom right, the wet lab itself. This is just an overview of the cargo capability of the vessel. The main crane on the left is as SWL, so a maximum load of 50 tons, 50 tons, and they can easily manage containers and ISO tanks up to 50 feet, so can also and up to 50 tons. The activity that foreseen for the next 2 years, at the moment we are on the berth in New Zealand. We are going to finish some maintenance activities and to enter in dry dock. Then we will start the preparation for the Antarctic mission 2021 that will be held in a short time, just practically focused on January and maximum February, other days of February 2001. Then we will move in Italy, and where we have major operation that we will carry out on the ship, because we install a lot of scientific equipment that I will describe later. And then we slowly start moving through the Mediterranean Sea, making some tests and some scientific activity in that basin, to be in Arctic in July, August. This is what we foresee to be there. We at the moment don't know exactly the operational area. We're waiting for to have hints from the researcher side. Then we will move again toward the Southern Ocean to New Zealand to perform a long mission in Antarctica in between 2021 and 2022. What we are going to implement now on the ship, be aware that the ship has been used by British Antarctic Survey for 20 years, but mostly used for cargo operation, not for research. Our idea is to implement anyway the research capability. To implement that, we need to have more instruments on board. So at the moment, just what we have on board are oceanographic winches, laboratories, and underway water samplings, obviously also offices. But the work that we are going to carry out in the spring 2021, we consider installation of high-resolution seismic, multi-channel seismic fishery facilities, implementing fishery facilities, and also multi-beam and super-to profiler and coring systems. In particular, this is the list of instruments that we are going to install. There are 2 multi-beams of Kongsberg, the 305 system. There's a full ocean depth system, plus a shallow water. We have this. We install also the EK80 fishing transducers, 6 transducer with different frequency to image the fish underneath the vessel. Super-to profiler T+12, also with Kongsberg, 2 different ADCP, 138 kilohertz, and the second one at 150. Multi-channel seismic will be installed a Sentinel 1,000-5,000 meters digital cable with M428 recording system. Piston corers and gravity corers, a piston corer up to 15 meters and 6,000 meters of wire, rosette carousel that we already used last year in Antarctica, and a go flow with cable for clean measurements that we also, it is already installed. And also installed are the standard meteor station with pyranometers and pyrgeometry and radiometers, and also the standard greenhouse gases concentration system measurement in continuous way on the ship. Practically, that's all that I would like to say to you. Is just to throw the stone into the lake to see if it can be something interesting for a vessel, having a vessels like that in the Arctic areas in next year, to see if there are potentiality for collaborations or use of the ship from your side. Thank you very much.
So thank you all the panelists for the presentation. That now we want to briefly summarize together with the colleagues the outcomes from the workshop of the last week. And basically, what I want to say is just resume what we have discussed last week. We have spoken about marine observations and marine infrastructures in Svalbard. So last Friday, we have presented some of the infrastructures that work around Svalbard. Most of them are located within fjords, where scientists and technicians spend a lot of efforts collecting data since many years, but there are also infrastructures that are located offshores and are important since they can connect processes that work in the fjords, which one that works offshore. Here you can see red dots that represent the infrastructures that were briefly presented last week, and also on the SIOS web page you can find most of the presentations in PDF format. You can have a look, and as you can see here also there are many infrastructures located in the Kongsfjord, and that is a large community of people working since many years, well organized, and in the Kongsfjord flagship, and they constantly interact each other to maintain and interact with the data and infrastructure. Other marine infrastructures in the SIOS network are the RX cruises and Argo Poland, provided by the Polish Oceanographic Institute, and the glider deployed along the West Spitsbergen current by in the area of West Spitsbergen by the University of Bergen, K-Lander by the University of Tromsø, the Cage Institute, Oceanographic buoy in Adventfjord, and the Fram Strait moorings provided and maintained since 1990 by Norwegian Polar Institute and Alfred Wegener Institute. Most of the observational facilities are included in the SIOS facility catalog, which are not still there. SIOS invites all research groups to register their infrastructure in order to make them more visible and more accessible in terms of metadata and data. So what were the motivations of the workshop in the last week? Were to connect the physical data with biochemical data and meteorological data, and together the picture was even more completed, because we have also an overview of the satellite data related to the sea ice distribution. Also, the numerical modeling is very important, since observations are fundamental to improve the modeling part, but also the numerical modeling outputs are really important to reproduce processes and within a large area, but also, as Kim Ullman reminded last week, they are also important to design new experiments in the oceanography field. So the workshop was thought to connect scientists working in maintenance, the marine infrastructure, and what we would like to discuss, we discussed it last week, we want to discuss today and in the next future, is logistical and technical needs, how to compare in an efficient way long-term measurements, how to fill the gaps, geographical gaps, but also instrumental gaps, parameters, optimize the data collation, and what arises from the presentation last week was also the importance of to have a constant data comparison among scientific actors around Svalbard. So we want to conclude this introduction with some questions that would summarize the main points we wanted to discuss and improve in the next future. So how to optimize marine infrastructures, and what is really needed to go forward, the next steps toward a more complete and coherent Svalbard marine infrastructures, which are them and which are the concrete actions we wanted to implement in the future. And finally, how to optimize logistics. We have an example today of an infrastructure, a ship, the Italian icebreaker Laura Bassi, but probably Inge would like to add that during the Polar Night Week there will be the possibility to discuss more in detail the logistics during the next summer, in order to give an overview of which opportunities will be open to the large community to have access to ship infrastructures, but not only, and have a chance to maintain the infrastructure during next summer. Right, Inga?
Yes, that's right. So during the Polar Night Week, we will have what's on the programme referred to as an open forum on the coordination of logistics. And this will be an opportunity for everyone who knows, for example, that they have spare capacity on their vessel that's planning to come to Svalbard, to make that available to the community and discuss other ways that we can work together to make logistics more efficient for the Svalbard region.